we will start a new chapter, that is momentum and forces in fluid flow. This is very important chapter because here we will develop the momentum equation and then how we can calculate the forces in fluid flow, so we can then study turbines and pumps. Now, learning objectives for this chapter. So after completing this chapter, you should be able to understand and apply the momentum equation. So up till now, we studied and extensively applied two important equations that you developed in your fluid mechanics 1, and we used extensively in solving fluid mechanics problems in fluid mechanics 2, clear, this course. So the third one, the first one is the continuity equation, which is based on law of conservation of mass, and the second one is the Bernoulli equation, which is based on law of conservation of energy. Now the third important equation is this momentum equation. This momentum equation we use whenever we want to calculate the forces in fluid flow. So this momentum equation we have used in development of some equations before, like in unsteady flow problems chapter. Now in this chapter we are going to develop this equation, and then we will apply this equation to solve problems that involve forces, clear. So after completing this chapter, you should be able to understand and apply this momentum equation, clear, which is based on Newton's second law. You will be able to calculate the fluid forces on pressure conduits. So as we studied about the pressure flow in conduits, pipes, etc. So in that case, if there is change of velocity in direction or in magnitude, or both in magnitude and direction, then forces will be developed. So you should be able to calculate these forces, and similarly to calculate the forces on a stationary and moving vanes or blades. So if a fluid is striking a vane, blade or plate, if it is stationary, how much force is exerted on that, and if water is striking a moving series of vanes, if there is interaction between the fluid and the moving vane, so then in that case the different forces you should be able to calculate. This is the case when we talk about the pumps and turbines. So in pumps and turbines we have a series of moving vanes or blades that are connected to the rotating element and that interacts with the fluid. So either the power is transferred from the fluid to the turbine blades, clear, or in case of pump, clear, energy is transferred from blades to the fluid so that we are able to lift the water, clear, because you add the energy to the moving fluid. So you should be able to calculate those fluid forces, clear. Now first we develop the momentum principle, and then we will apply this momentum principle to different fluid flow conditions, and we will be able to calculate the forces. For this case, you can see here, this is a system, a fluid system, which is shown here. So the system, it moves, clear, you can see here the system moves, and in here at a distance, at the section 1 here, there is an inflow of the fluid and there is an outflow from the fluid at section 2. So you can see here that at time t plus delta t, so you can see that this is the moving fluid system S. So the system moves and it covers a distance delta S1 at this point and delta S2 at the second point. Clear? So this is the system. If you have defined the system in your fluid mechanics 1, so the second thing here is the control volume. So the control volume, which you can see here, control volume is a fixed region in space. This is the definition which is given in your textbook. So control volume is a fixed region in space. It does not move. Clear? But anyhow, this is in general true for many fluid mechanics problems, that we consider the control volume to be stationary, fixed in space. But there are certain situations where we can also consider a moving control volume to make the problem analysis simplified. Clear? But anyhow, according to our textbook, it is a fixed region in space. So now, why we consider this control volume? Because it helps us to analyze the problem. It simplifies the analysis. Clear? That's why this concept we use in fluid mechanics analysis. Now in this case, you see that this control volume here, it contains the fluid at time t, and then there is an inflow of the fluid, clear, at this point here at section 1. And as you already know that we have these streamlines here, so there cannot be flow across the streamline. So that's why the fluid can enter and leave this stream tube. Clear? This stream tube, which we show here in the form of this control volume. So in this case, the fluid can enter and leave at the ends. So now what we do is that we consider this control volume for a steady flow. I will explain what is the steady flow and unsteady flow, how we can consider this momentum principle. So commonly we will develop this for the steady flow. I will tell you if you want to apply to unsteady flow, then what we should consider. So in this case, we have a control volume for steady flow with control surface, clear, cutting a constant velocity stream at right angles. Control surface here, clear. Similarly, control surface here at section 2. So now we consider this velocity v1, and also because we are deriving a general expression, so let's say the fluid has a density v1 and also the cross-sectional area is a1 at section 1. And at section 2, then we have the density as rho 2 and we have the area is a2. So the momentum principle that is derived from the Newton's second law. We will use the Newton's second law to derive this momentum principle. And what is the Newton's second law? That F is equal to ma. Summation of F means all the forces that is acting on a body is equal to mass into acceleration. Clear? F is equal to ma. Now this can be written as, because acceleration, it is the rate of change of velocity. So this can be written as summation of F is equal to d by dt into mv. And what is this mv? The product of mass and velocity. So this is momentum. Clear? So this is rate of change of momentum. So it means that if we want to calculate the force, this is the force, external force acting on a body of mass m produces an acceleration in the direction of force. So if we want to calculate this force, we need to calculate the rate of change of momentum of that fluid body. This is what this equation says. If I want to calculate the force, I need to calculate the rate of change of momentum. This is momentum, m into v, and divided by dt, it is the rate of change of momentum. So now the next question is that what is the rate of change of momentum for fluid? So that we would like to calculate, so that we can simplify an equation that we can easily apply to calculate the forces in fluid flow. So this equation states that the sum of the external forces on a body of fluid or system is equal to the rate of change of linear momentum of that body or system. It means that the sum of external forces, so that is equal to the rate of change of linear momentum. Clear? And the change in momentum must be in the same direction as the force. Now let us see that how we calculate this rate of change of momentum. So from this equation, we can write down summation of F into dt, that is equal to d into mv. So as you already know that, and we studied in the unsteady flow chapter also, that this force into short time interval dt, this is impulse, and d into mv, this is the change of momentum. So that is impulse equals change of momentum, and we sometimes use the terminology impulse momentum principle. So we sometimes call it as the impulse momentum principle. Now to determine the rate of change of momentum for a fluid, consider a stream tube as shown. We consider a stream tube. Now in time dt, volume entering stream tube. How much fluid volume is entering the stream tube? As I write down here before, let's us assume that we have this as rho 1 into A1 at section 1, and in here we have rho 2 into A2, and we have V1 and V2. Clear? So if we consider these parameters here, now we can easily calculate how much is the volume that is entering the stream tube here. So this will be simply equal to area into distance. So area at this point here at section 1, it is area A1, and the distance, so this is delta S1. So we have S is equal to Vt. So in time dt, because it moves at time dt, so this is equal to V into T, and this can be written as V1 into dt. So this is what it comes here. S is equal to Vt equal to V1 into dt. So now volume entering stream tube, that is equal to A1 into V1 dt. Now this volume has mass. So mass entering stream tube, that is equal to density into volume. So we already know that density is equal to mass into volume. So from here, mass is equal to density into volume. So volume we already calculated here, that we already calculated from here, and multiply by density of the fluid at section 1. So that is rho 1. Now momentum of the fluid entering stream tube. So momentum is what? It is the product of mass and velocity. So we have mass into velocity. Mass we already calculated, and into this velocity v1. Now this is the condition at section 1 here. At this section 1 here, so we have calculated momentum of fluid entering the stream tube. If we proceed like this, volume entering the stream tube, then mass entering the stream tube, then momentum of fluid entering the stream tube for section 2. If we proceed for section 2 in a similar fashion, so what we get? We get that momentum of fluid leaving stream tube, that is equal to mass into velocity, and it will be given by this expression. Now what is the change of momentum? The net change in the momentum. Clear? We consider the inflow and we consider the outflow. So summation of forces, as we write down here, this summation of forces. So this is equal to the rate of change of momentum. This is what it says. This is equal to the rate of change of momentum. Clear? So what is the rate of change of momentum? This is the change in momentum divided by time. So what we can write down here is rate of change of momentum. So it will be the difference of the two, momentum of fluid leaving the stream tube minus momentum of the fluid entering the stream tube divided by the time. So this becomes this one is the change in momentum. In the numerator we have change in momentum divided by dt, rate of change of momentum, divided by dt is rate of change of momentum. Now in this case here, what we have considered is that we are considering the momentum of fluid entering the stream tube and momentum of fluid leaving the stream tube. But we did not consider what is the momentum of the fluid contained within this control volume. Within this control volume, what is the momentum of this fluid within this control volume? So if I can write down here along with this is plus another term, and that is equal to d by dt. This will be equal to d by dt into product of mass and velocity here, and this is the rate of change of momentum within the control volume. This is within the control volume. Remember, this is within the control volume. So now in this case, then this equation is applicable to unsteady flow. Then this is applicable to unsteady flow. So now that we consider also the rate of change of momentum within the control volume, we have the rate of change of momentum. Clear? This is the momentum of fluid entering the stream tube. This is the momentum leaving the stream tube. And also we consider the rate of change of momentum within the control volume. Clear? So then in this case, this is the applicable to unsteady flow problem. But if we neglect this rate of change of momentum within the control volume, if we ignore this, then it is applicable only to steady flow. Then it is the steady flow. We say that there is no rate of change of momentum within the control volume. So if we ignore this term, then in that case, this equation is then applicable for steady flow. But if we consider this term, then as a whole, it is applicable for unsteady flow. So it means that for steady flow, the net force on the fluid mass is equal to the net rate of outflow of momentum across the control surface. So it means that for unsteady flow, the net force, clear, on the fluid mass, that is equal to the net force on the fluid mass, that is equal to the net rate of outflow of momentum across the control volume. So now from continuity, we have Q is equal to A1 V1 is equal to A2 V2. And if we consider the fluid of constant density, then in that case, we can write down rho 1 and rho 2 is equal to rho, and then this equation for steady flow, then it becomes summation of F is equal to rho Q into V2 minus V1, or rho Q. What is rho Q? It is the mass flow rate. This rho Q, it is the mass flow rate into the change of velocity. This is for steady flow, and the direction of F must be the same as that of the velocity change delta V. Now, summation of forces, if we want to calculate the forces in fluid flow, that is equal to rho Q into delta V. This is the rate of change of momentum. How? Because you can see here that this rho, this can be written as kilogram divided by cubic meter. We have discharge. Discharge can be written as cubic meter per second. And what is velocity? Velocity is meter per second. Now this cancel out with this, and what we are left? We are left with kilogram mass into the velocity here. So this is momentum, and then divide by the second, rate of momentum. So that's why this rho Q delta V, it represents the rate of change of momentum. So now what we were looking for? We were looking for that if I want to calculate the forces in fluid flow, what is the rate of change of momentum? What is that rate of change of momentum? So remember, in fluid flow, this rate of change of momentum is what? This rate of change of momentum is rho Q delta V. This is the rate of change of momentum. So if we have a fluid of mass density rho and it is flowing with a discharge Q and there is a change in velocity, we can calculate the forces that will be generated. So remember, for fluid flows, if you want to calculate the forces in steady flow, you just simply need to calculate this quantity here. And this quantity rho Q is the mass flow rate. Clear? It is the mass flow rate, and delta V is the change in velocity. So note that this summation of F, it represents the vectorial summation of all forces acting on the fluid mass in the control volume, including gravity forces, shear forces, and pressure forces. So all the forces that we can consider due to the weight of the fluid mass, due to the shear forces that are generated, and the pressure forces, all these forces will be in this summation of forces. So any one of the force we can calculate, provided other quantities are given. So this summation of forces, it is referred to all the forces. Clear? That include gravity forces, shear forces, pressure forces, including those exerted by the fluid surrounding the fluid mass under consideration, as well as the pressure forces exerted by the solid boundaries in contact with the fluid mass. So we will see in the problems how we consider these forces summation, and then we calculate the rate of change of momentum. Now, if we have a three-dimensional flow in the x, y, z direction, then the above expression can be written as summation of fx, and this is equal to rho q into change of velocity in the x direction. So if we have flow in the y direction, then summation of forces in the y direction will be equal to rho q into change of velocity in the y direction, and similarly for the z direction. So if we have a two-dimensional flow, let's say xy plane, you just consider here. If we have yz plane, you consider these two. And if we have x z plane, you consider these two equations. And if we have a three-dimensional flow, so then in that case we have to consider all the three forces. This will be the components of the total force. And if, for example, we have a two-dimensional flow field in xy, so you will calculate the x component of the total force using this expression, the y component of the total force using this expression, and then we can calculate the total force by application of the Pythagoras theorem, because the total force, then this will be equal to, for a two-dimensional flow, this will be simply equal to summation of fx square and plus we have summation of fy whole square. So this way we can apply the this Pythagoras theorem to calculate the total force for a two-dimensional flow, and you can also calculate orientation of this force. So this we will see when we solve the problems. So this is for a steady flow that we have developed these momentum equation, momentum principle. Clear? So this is the equation, again the third fundamental equation beside continuity and Bernoulli equation that we can use to calculate the forces in fluid flow. Now we apply this momentum equation. So in common application, the momentum principle, we use it to find forces that flowing fluid exert on structures open to the atmosphere like gates and overflow spillways. So you already see that we have water flowing in channels, streams, rivers, and we construct different type of structures for different purposes, clear, such as dams, gate structures to control the flow. So then in that case, because they retain the water, so the water will then exert forces on these structures, for example the gates, etc., and the water overflows the spillways. So this we can apply the momentum principle to calculate the forces, because this is important aspect, and then we analyze and design these structures to withstand these fluid forces. So let us solve an example to see the application of momentum principle. So now in here we consider a gate structure, which you can see raise the water level, and then under the gate the water is allowed to flow. So the question is that, this is from our textbook, the question is that find the horizontal thrust of water on each meter width of the sluice gate, which is shown here. Y1 is given 2.2 meter, this is Y1. Similarly, Y2, that is given as 0.4 meter, this is Y2 here. And Y3 is the depth of water below the gate, this is Y3. So now we are going to calculate the horizontal thrust of water. Remember this equation that we developed, this is the some external forces which are acting on the fluid. So this equation will give us the external force. Now if we want to calculate what is the force of water on the gate, that will be equal and opposite to this. This is how this equation works, that this will be the external force on the fluid, then the force of fluid on that body which exert force, that will be equal and opposite. So this is how we calculate the forces. So this will be equal to, let's say that we assume, clear, a force here, that let's say this is the assumed direction, that this is the force. So this force, either it can be denoted by Fx because in the horizontal direction, or it can be denoted by force of gate on water. This is the force of gate on water. This I have to calculate using this equation, the external force. but we are asked to calculate the force of water on the gate. That will be equal and opposite to this. Once we calculate this, this is the external force on the water, then the force of water on the gate will be equal and opposite to this. Clear? So this direction is assumed. We don't know. This is how you will solve the problems. We will assume this direction here. For example, in this case, we are assuming the direction of this Fx towards the left. It is acting to the left. Clear? So this is the assumed direction. In the end, the sign will tell us that this is correct or not. So in the first case, we will assume the direction for the forces. What could be the other force? For example, this I consider for this gate, I consider this as my control volume. Clear? This is my control volume. So now on this control volume, you see there are external forces acting on this control volume by the fluid. And what are those external forces? Those external forces are the hydrostatic pressures in this case. You can see here that if I draw here, so on this side of water, we have this pressure here. And similarly, on this side of water, it will also exert a pressure. So resulting in this hydrostatic pressure diagram. So you see that this will be a force which is acting on this control volume. So this will be F1, and similarly there will be a force here. So this will be F2. So now you can see that these are the external forces acting on this control volume that we have to consider in the momentum equation. So before we consider the forces, we need to calculate the velocity and the discharge also. So for that case, because it is asked that find the horizontal thrust of water on each meter width of the sluice gate, it means that this gate which is shown here, it has a width, just like you studied is notches and wear. This is the gate which is shown here, so it has some width. So this is the width of this gate. So now it says that you just consider unit width, 1 meter width of this gate. This is the unit width of this gate. This is what it says, each meter width of the sluice gate. So on this 1 meter width of the gate, how much force is acting, that you calculate on this 1 meter width of the gate. So on this 1 meter, what is the force acting, that we need to calculate. So in order to calculate that, we have to calculate now the discharge per unit width. Small q is the flow rate per meter of width. So this is cubic meter per second per meter. We have the total discharge, and let's say the width of the gate. So let's say, for example, the width of the gate, that is B or L, whatever you consider. The width of the gate is this B. So this Q divided by B. So this will become discharge per unit width. Clear? Because this will be equal to cubic meter per second per meter. So this is how this small q we represent. Discharge per meter of the width per unit meter, because we are calculating the force for a unit width of the gate. Clear? So that's why we calculate the discharge as the unit width. So now from continuity, what we can write down, Q is equal to V1 into Y1 equal to V2 into Y2, because it is discharge per unit width. So that's why velocity into Y1 into 1. So that's why we just write down V1 into Y1. This is cubic meter per second per meter. So now from here, y1 and y2 are given. Discharge. Clear, we can express V1 is equal to Q divided by 2.2. What is 2.2? That is Y1. Y1 is 2.2. And similarly, V2 is equal to Q divided by 0.4. What is 0.4? Y2. Y2 is 0.4. So V1 divided by Q, Y1, and then V2 is equal to Q divided by Y2. Now we can write down the energy equation, neglecting the friction, because it is given in the question, you neglect the friction. So now neglecting the friction, we can write down what is the equation that we can write down for this channel. We have the depth of water, so hydrostatic pressure, that is due to the depth of water, and then we have the velocity head. Fluid is flowing with a velocity v1 at section 1. Let's say this is your section 1, and in here this is your section 2. So this will be v1 square by 2g. This will be equal to y2 plus v2 square by 2g. This is v2 square So this is the equation that we write down. So this is y1 and this is v1 square by 2g. This is y2 plus v2 square by 2g. So now in this equation, the only unknown is q. So q you can calculate easily. The only unknown is q. So q you can calculate once q is known. So this q we can put here to calculate v1 and v2. This q you can put here to calculate v1 and v2. Now we have the velocities. So now we will be able to calculate the change in velocity. This is what is required in the momentum equation, change of velocity. Clear? So now in this case, first we have to now write down the momentum equation, which says that now because we consider the horizontal thrust of the water, so we consider summation of Fx, that is equal to rho q into v2 minus v1, change of rate of change of momentum in the x direction. Clear? So as I said that this summation of forces, this is actually sum of all the external forces. So that's why if I can quickly draw them again, one was this force here. So this is your F1 here, this is F1. One was this force. So this is your F2. And then we consider the external force, that will be the, let's say for example, Fx, or it can be force of gate, or it can be force of gate on water. This is assumed direction. We don't know. In the end, the plus minus sign will tell us that this assumed direction is correct or not. So remember, this is always the case. We will assume the direction. So this is assumed direction. So now we write down F1 minus F2 minus Fx, because we consider in this direction the force to be positive. That will be equal to the rate of change of momentum in that direction. Clear? So now you just put the values. You see F1 and F2 you can calculate. How to calculate this? For example, this F1, we already know that this dimension here you already studied in mechanics of solid and structure analysis. This here, this will be equal to gamma for water this will be equal to gamma into y1. So now if I want to calculate the force F1, the equivalent point load, this is what you try to calculate in your mechanics, strength of material, solid mechanics, mechanics of solid, or in structure analysis. This is what you are commonly do to convert a triangular load into the equivalent point load. So what you do, you calculate the area of this triangle. So the depth is y1, and this ordinate according to fluid mechanics principle, that is gamma into y1. So what will be the area of this triangle? That will be your F1. So what will be F1? This will be equal to half triangle area, half into base into perpendicular. So this will be equal to half into y1 into gamma y1. And then from here, this is equal to gamma into y1 square divided by 2. Gamma into y1 square by 2. This is what we have written here. Gamma into y1 square by 2. Gamma into y2 square by 2. Similarly, you already also studied in your fluid mechanics 1, clear, in fluid statics, when you calculate the force on plane area. So this is a plane area because we consider unit width of the gate. So for unit width of the gate, what will be the area? This is the unit width. If I show you, this will be a rectangle. Clear? So this is the unit width of the gate that we consider. This is the unit width. And for that, we have to consider the depth of water. So that is your y1. Now, if I want to calculate the force which is acting of the fluid against this rectangle, for this we need to calculate the centroid of this area. So what will be the centroid of this area? Since it is a rectangle, so it will be y1 by 2. This will be equal to y1 by 2. Now you already studied in your fluid mechanics that F is equal to the total force which is acting on this. That will be equal to gamma into HC, means the depth of centroid, into area A. So what we have this gamma. What is the depth of centroid? y1 by 2. So this is your depth of centroid of the area, y1 by 2. And what is the area? y1 into 1, because we consider the unit width, y1 into 1. So now from here, what will be the force equal? Force will be equal to gamma y into y1. That will be equal to y1 square divided by 2. So you can see here we get the same expression here as you can see here, this one. So any formula you can apply to calculate these forces. Now we calculate the force from here. The only unknown is this Fx, or force of gate on the water. So now we can calculate Fx as 11,000 Newton per meter. Now in this here you can see we get plus sign. We get plus sign, so it means that the assumed direction of this Fx is correct. What was the assumed direction? To the left. We assume this acting to the left. So in the end we get plus sign. So it means that this assumed direction of the force is correct. Clear? Then equal and opposite is the force of water on the gate. So what will be the force of water on the gate? That will be equal and opposite to that. This is how we calculate the force of fluid on the body. So the force of water, let me write down water on the gate. So that will be equal and opposite to this force. Because in the momentum equation, according to Newton's second law, that F is the external force. So that's why we calculate the external force on the fluid, and then force of the fluid on the structure will be equal and opposite to that. So force of water on the gate, that will be equal to 11 kilonewton acting to the right, equal and opposite to that force. So you can see that we applied the momentum principle and we are able to calculate forces acting on hydraulic structures. So it's very useful, momentum principle. Clear? Next, we consider forces on pressure conduits. So how forces are developed in pressure conduits? Because, for example, in this case, what the
Excuse me, sir.
momentum, yes,
सर ये क्यू पे नहीं समझा, ये क्यू कैसे आया सर? क्यू तो हमें क्वेश्चन में नहीं किया मैंने।
Q हमने कैलकुलेट किया, this we have calculated here using the continuity equation and then using the energy equation. From here we calculated this Q. From where this U comes, we consider the continuity equation and then we apply the energy equation, so we calculate this Q. Once Q is known,
ठीक है सर, ठीक है
then
सर।
you can calculate V1 and you can calculate V2. Now forces on pressure conduits here. So we have, let's say, a larger diameter pipe here, and that we want to connect to a smaller diameter pipe. So how you connect this? This is just an example. So in this case, when we want to connect a larger diameter pipe with a smaller diameter pipe, so we provide a reducer. This is a reducer. This is what you see here, which is shown in this diagram. So this reducer we provide here. Now you can see that velocity is V1. Now that we connect this to a pipe which is a smaller dia, the velocity will change to V2. So now there is change of velocity. So when there is change of velocity, there will be force. Because what we write down, that summation of F that is equal to rho Q into delta V. So when there is change of velocity in direction and in magnitude, there will be force. So now that because the velocity changes from low velocity to higher velocity, so it means that there will be force acting by the fluid on this reducer. So this is known as reducer. This is what you can see here. This is reducer. We connect. This is just an example to understand force on pressure conduits. So we consider this reducer. Connect the larger pipe diameter with a smaller pipe diameter with the help of this reducer. So now to calculate the forces, clear, we consider the case of horizontal flow to the right on the reducer. Why we consider the horizontal flow? So that we neglect the weight of the fluid. This is the free body diagram for the forces here is shown here. So this is the control volume. This we considered as the control volume. This is my control volume. Now in this control volume, we have this force as acting force of reducer on the fluid. Because I said these are giving us external forces. The force of fluid on reducer will be then equal and opposite to that. Now this force of reducer on the fluid, this is the assumed direction. In the end, the plus minus sign will tell us that it is correct direction or not. So similarly, we have fluid mass on both sides of this control volume. That's why you can see here that we consider the pressure forces in this both the directions. Clear? Now the flow is horizontal, so it means that the weight of this fluid we can neglect because this fluid has weight. So because we consider the flow in a horizontal plane, it means we are looking to this from the top, and this is XY plane. This is XY plane. So it does not mean that this is vertical. So this is XY plane. So that's why in this case we just consider only this direction, a horizontal. So that's why what is the advantage of that? We can ignore this weight. Similarly, there will be shear stresses here, shear forces that can generate, but those shear forces we neglect. Why we neglect these shear stresses or shear forces? because this length is very small. If length is very large, for example, we have a pipe whose length is very large, this control volume was, let's say, a large length, then in that case the shear forces will be significant. But here this length is very short, so the shear forces that can be neglected. So remember, in addition to these three forces, there can be gravity forces, there can be shear forces. But since we consider the flow in a horizontal plane, the weight can be neglected. And because length of this reducer considered here is very small, so that's why even though if shear force is there, it will be very small. So it's better to neglect and simplify the analysis. So that's why we only consider these forces here. Now a free body diagram of the forces acting on this fluid, that is shown. Clear? Already I explained the free body diagram of the forces acting on the fluid mass in the reducer. We consider this control volume. So now because the flow is in a horizontal and there are no components of y, we consider the forces in x direction. So summation of forces in x direction will be equal to the change of momentum in the x direction. So what are the forces? Summation of forces. So this summation of forces, this will be equal to P1 into A1, this is the force, minus P2 into A2, this is the force, minus force of reducer on the fluid acting in this direction, will be equal to the rate of change of momentum, rho q into v2 minus v1. Final velocity is v2. From this side at section 1 the velocity is v1, so v2 minus v1, that will be the change in the velocity in the x direction. So now if you simplify this, so force of reducer on the fluid, that will be given by this expression. If we are given the values, then we can put the values and we can quantify the value of this force of reducer on the fluid. So this will be the force of reducer on the fluid. What will be the force of fluid on the reducer? So the force of fluid on the reducer, that will be equal and opposite to that. That will be equal and opposite to this force here. This will be the force of fluid on the reducer. So that will be equal and opposite to this force. So this equation, it gives the net force of reducer on the fluid in the x direction. This force x to the left is assumed because we can get plus sign. And the force of the fluid on the reducer is equal and opposite to that of reducer on the fluid as I shown here. So basically from this momentum equation, the force we calculate, that is external force on the fluid, and then the force of fluid on that surface or body or system which is asked, that will be equal and opposite to that force. So this is how you see we can calculate the force if we consider the case of a reducer. Next we consider force on the fluid in a reducing band. For example, here you can see that we have a pipe on this side that is connected to again a smaller diameter pipe with a reducing band. You see that the cross-sectional area of the band is reducing. So then in this case, again in the previous case, what was the situation? We saw that whenever there is a change of velocity, so you see there was a change of velocity magnitude, still the forces are developed. Now in this case, in case of reducing band, the velocity is changing in magnitude and direction both. Clear? If the fluid undergoes a change in both direction and velocity as in the reducing pipe band shown here, again forces will be generated. And it's not only reducing band, even if this reducing band was not reducing, let's say we have this pipe and then you connect to the vertical pipe with this bend here, you see in this case the velocity is changing in direction. again there will be a force developed, and the force of water on the bend will be equal and opposite to this force. So remember, whenever there is a change of velocity in magnitude or direction or both, then in that case forces will be developed. So now in this case, for a reducing bend, how we calculate the force? So the force will have two components because now it has xy components. So in this case, we see that this can be the x component here, and then this will be the y component here. So that's why the force has two components. We will consider the x and y direction, and then we can calculate the total force acting. So for this case, in the x direction, we will consider this momentum equation. Summation of forces in the x direction will be equal to the rate of change of momentum in the x direction, delta Vx. So now what are the forces acting? One is P1 into A1. This is acting in the x direction. It has no y component, so that's why it is P1 into A1. Now you can see here this A2 and V2, it is making an angle this theta. So since it makes an angle theta, so we can calculate this. This is the force here. So this is your P2 into A2, and it makes an angle theta. So there will be two components of this. So one will be this component here. So that will be equal to P2 into A2 sine of theta. Sine is always opposite to the angle, sine of theta. And another one will be this component here. That will be equal to P2 A2 into cos of theta. So now you can see that it is acting in this direction. That's why minus P2 A2 into cos of theta. And also this force which is acting here is also, this will be the force of bend on the fluid, the total force. So it will have two components. What will be the two components for this force here? One will be this component here in the x direction. So this will be force of bend on the fluid in the x direction. And similarly, another one will be this force. This will be force of bend on the fluid in the y direction. So that's why we consider this as minus force of bend on the fluid in the x direction. And this will be equal to the rate of change of momentum in the x direction. So V1, this is your V1, it is acting in this x direction here. But you can see that V2, it is also making an angle of theta. This is V2. So what is V2? This is your V2. So it also has two components. One is this component, one is this component. It makes this as theta. So we have this V2 cos of theta, and this is equal to V2 sine of theta. So that's why in the x direction, rho q is equal to V2 cos of theta minus V1. So we can simplify this if values are given for V1, V2, theta, P1, P2, A1, A2. We can calculate the force of bend on the fluid in the x direction. Similarly, in the y direction, so we use this equation, summation of forces in the y direction, that is equal to the rate of change of momentum in the y direction. So now P1A1 has no component in the y direction. That's why it is 0. And minus P2A2 sine of theta, because you can see here this one, P2A2 sine of theta, acting down, so negative. That's why this is equal to minus P2A2 sine of theta. This one is acting up, force of bend on the fluid in the y direction, so it is plus, and then the rate of change of momentum in the y direction. V1 has no component in the y direction, so 0, and in the y direction this is V2 sine of theta. This is here V2 sine of theta in the y direction, so V2 sine of theta. Now you can easily simplify for force of bend in the y direction. So if values are given, you can calculate the numerical value for this force. Now if we want to calculate the total force, this is now the total force acting. Now its components are known. We can easily calculate the total force by application of the Pythagoras theorem. We can apply the Pythagoras theorem and we can calculate the total force, and also we can calculate its orientation, alpha. So alpha will be equal to tan inverse force in y direction divided by force in x direction. So this is the force which is exerted by bend on the fluid, but we are interested to calculate force of fluid on the bend. So that will be equal and opposite to this. What will be the force of the fluid on the bend? This will be equal and opposite to this value. This will be force of the fluid on the bend. And similarly, you will have its y and x components, and also its orientation, that alpha will be same as this, calculated by this equation here. So this will be force of fluid on the bend in y direction, and this will be force of fluid on the bend in the x direction. So the total force of fluid on the bend exerted by the fluid on the bend is equal in magnitude but opposite in the direction to the force of bend on the fluid. So this is how we calculate the forces on pressure conduits. Clear? Next, we consider force of a free jet on a stationary vane or blade. So we simplify this and understand by solving this problem. This is problem from the textbook. So how to calculate now force that is striking a stationary vane or blade. If the vane, blade or plate, whatever you call it, if that is at rest, how much force is acting on that vane, blade or plate by the free jet of water. So in this case, what is happening, this vane is at rest and free jet of water flows over this vane, because you can see there is change of velocity in magnitude and direction. So there will be force exerted on this vane. How much is the force exerted that we want to calculate? So a free jet of water with initial diameter 2 inch, the diameter of this jet here, cross-sectional diameter, that is 2 inch. It strikes the vane as shown in the figure. Now theta is 30 degree and V1 is 100 foot per second. This V1 here, this is 100 foot per second. Now due to the friction losses, as the fluid flows over this vane, the velocity is reduced to 95 foot per second, from 100 to 95 foot per second. And flow occurs in a horizontal plane. It means this is horizontal plane. XY plane is horizontal. Why? For this case, then weight of the fluid we can neglect. What is the weight of the fluid that we can neglect? So that's why we consider, for simplicity, the flow to occur in a horizontal plane, because if you consider in a vertical plane, then weight of the fluid you need to consider for accurate analysis. So flow occur in a horizontal plane. Find the resultant force on this blade. So on this blade or vane, how much is the resultant force acting, that we need to calculate. So we have to apply the momentum principle or the momentum equation. So how to do that? Because the flow occurs in xy plane, it will have two components. So the forces Fx and Fy represent the component, and this is directions are assumed. We are assuming that Fx acts to the left and Fy acts in the upward direction. These are assumed direction. Remember, in all the problems we will assume the direction of unknown forces, x, y, z direction. Then in the end, the sign will tell us that these assumed directions are correct or not. So we assume the directions, and the net force that is acting on this vane, which exerts on this fluid, because these external forces we calculate due to the momentum equation, and then force of the fluid on the vane will be equal and opposite to that. So their resultant force, that will be, in this case, the two components, and then this will be the resultant force. This will be the force of blade on water. So now we consider the momentum equation in x direction to calculate the forces. So this Fx summation of forces, that will be equal to change of momentum in the x direction. Clear? So now in this case we need to calculate the discharge. So we need to calculate the cross-sectional area. The area of the jet of water is 2 inch. So pi by 4 into d square, keep the units consistent. So this is the area, cross-sectional area of the jet of water. Now in this case, the external forces is only this Fx, no other force that we can consider. This is the free body diagram. So that's why minus Fx, because it is opposite to this plus x direction. So minus Fx is equal to change of momentum in the x direction, v2x and v1x, these are given. You see here, v2 is 95 and v1 is 100. So what we say here is 100 in the x direction, but in this v2 it makes an angle theta. So that's why in the x direction, what is its component? We have v2 and it makes an angle theta, which is given 30 degree. So this is theta. Now it will have two components, one in x and one in y. So this will be equal to v2 cos of theta, and this will be equal to v2 sine of theta. So now that's why we have v2 cos of theta in the x direction. That's why v2 cos of theta minus v1. So we can calculate the value of this force, and F comes out to be plus. So now that I get plus sign for the F, this minus cancel out with this minus. It means that this assumed direction is correct. If I get negative answer, let's say I get minus 75, then that would mean that the assumed direction is incorrect. It is in this direction. This is then the correct. This is incorrect if I get negative answer. But since I get plus answer, it means that the assumed direction is correct. This assumed direction is correct. Next we calculate, the plus sign indicates that the assumed direction of Fx was correct. Next we apply the momentum equation in the y direction. So summation of forces in the y direction will be equal to the rate of change of momentum in the y direction. So in that case, we have only this plus Fy acting, no other external force. So plus Fy acting, and the rate of change of momentum in the y direction, v2y minus v1. So v2y, what is v2y here? v2 sine of theta. This is v2 sine of theta. So that's why this is written here v2 sine of theta. But this y v1, it has no component in the y direction, no component. That's why it is 0. So now from here, Fy is 201 pound. Again I get plus answer. It means that this assumed direction is correct. If I get plus answer, this assumed direction is correct. If I get negative answer, then it means this direction is incorrect. It means it is acting down, not upward. So we assume the direction of forces. In the end, the plus minus sign tell us that the assumed direction is correct or not. Now that we have calculated the two, yes, what is the question? Is there any question? Okay, so now we have calculated the two component of the forces, we can calculate the total force. Clear? So the total force we can easily calculate, that will be due to application of the Pythagoras theorem. So you can put the values, and this is 214 pounds. And we can also calculate orientation of this force, which is alpha. Now alpha will be equal to tan inverse force in y direction divided by force in x direction. So theta is 69.5 degree. Now this is the force of blade on water, but it is stated find the resultant force on the blade, means find the force of water on the blade. So that will be equal and opposite to this. What will be the force of water on the blade? That will be equal and opposite to this. This will be the force of water on the blade. Equal and opposite to this. The force of the fluid on the blade is equal and opposite to this. And also its orientation. This will be alpha. That's why you can see here it is in this direction. So even if I draw a horizontal line here, you see this is force of water on the blade, makes this is alpha. Even if I draw a horizontal line here, this will also be alpha, because these two are alternate angles. So that's why it is shown here like this, making an alpha of 69.5 degree with the horizontal in the clockwise direction here. Clear? So this is how we calculate force of water on the bend will be equal and opposite to this, and this will be the y component, same as this Fy, force of water on the blade in y direction, equal and opposite to this, and this will be force of water on the blade in the x direction. So this is how we apply the momentum equation. We can calculate the force on stationary vanes, blades or plates.